To help carry on our important work, I want you to join the secret squadron and wear this official badge and have this secret decoder.
My name is Brian McLoone. I'm a visiting fellow at the Center for Philosophy of Science, and the project that I'm working on concerns modeling and idealization in science. And in particular, what I'm interested in is how to formally represent the sorts of reasoning processes that a scientist is engaged in when they're thinking about some highly idealized, abstract model. So when they're thinking about a model like Lotka-Volterra, a classic model, where you've got a prey population like foxes and a predator population like rabbits, and they're interacting with each other and oscillating. I'm interested in thinking about what tools from logic can we use to capture that sort of reasoning. Why do we care about this? Well, I think there are two reasons. One is we might just be interested in developing a sophisticated model of how scientists reason, and we can use resources from logic to do so. Another reason is that we might be interested in programming an AI to reason in a comparable manner, and that too would probably need to draw on resources from formal logic. And so, okay, so what logic do we need to capture how scientists reason about models? Well, generally, with a model, at least one of the assumptions is false. In fact, every model that I've ever come across has at least one false assumption. So if we're taking Lotka-Volterra, for instance, the standard presentation of it is that it's a deterministic model, which means that the noise of the system has been washed away by taking population size to infinity. So that's a false assumption, that the populations of predators and prey are infinitely large. Another false assumption that I'll talk about in a bit is that the predator and prey populations don't just come in integer values. So you don't just have one rabbit or two rabbits, 3 rabbits, and so on. You can have 1.74 rabbits or pi rabbits. So that's another false assumption. So it seems like what we might want to do here is, if the scientist knows that these assumptions are false, they're not true of any actual system, then we're going to want to use some sort of counterfactual logic to capture what they're doing. So essentially the model says, if some population were like such and so, then the dynamics would be like such and so. And so a little bit more specifically, we can think of a model as a counterfactual, in which we've got the assumptions of the model and the antecedent, and the predictions and the consequent. Okay, so far, so good. But a complication emerges because it seems like, in some cases, the assumptions of the model are impossible. So the example that I'm most interested in is that when you're using calculus to model the dynamics of some population, you have to assume that the size of the population is a continuous quantity. So for instance, with Lotka-Volterra, as I said, you have to assume that the sizes of the rabbit and fox populations, or the predator and prey populations, are continuous quantities. This is necessary to do calculus. But if you think that it's just impossible, it's not just false, but impossible to have, say, pi number of rabbits in some population, then that means there's not going to be any possible world at which the assumptions of the model are satisfied. Now, a standard view in counterfactual semantics is that if you've got a counterfactual in which the antecedent is false at all possible worlds, that makes the whole counterfactual vacuously true. This is the so-called Acuity Thesis. I think the Acuity Thesis is wrong, because this just isn't how we think about models in science. So if we do think that the assumptions of Lotka-Volterra are false at all possible worlds because it assumes that rabbits can come in non-integer values, it doesn't seem to be the case that anything we say about Lotka-Volterra is just vacuously true. It seems like some things we could say about Lotka-Volterra are not vacuously true. They're predictions that follow, say, mathematically from the assumptions. And moreover, it seems like we can say things about logic of Voltaire that are false. So if we say that if the assumptions of logic of Voltaire are met, then the rabbit population will eventually go extinct, that just seems false. And the Acuity Thesis doesn't allow us to say that. So what I've been working on is developing some extensions to modal logic using impossible worlds to help us capture how scientists reason about models that have these impossible assumptions. And I've been expanding this recently to include some experimental work with scientists. So we've asked scientists, whether they think that it's impossible in a metaphysical sense for rabbits to come in non-integer values, and we're interested in how that affects or doesn't affect what they say does and doesn't follow from some model. And so this project brings together a few different strands. You've got formal logic, you've got psychology, and you've got these theoretical models in science, and I'm trying to make sense of them all. Thank you.